help with that. We are going to go straight into our lesson now about classifying triangles and trying to keep this lesson as short as we can. Okay, so when we talk about classifying triangles, we're basically talking about naming triangles. And there's two main ways that we do that. We name triangles or classify triangles either by what their largest angle is, or by their sides, how long their sides are. Okay, so if you turn to page 542 now, with your special paper in front of you, your pencil, eraser, your book, of course, you also need, what else? Pencil, eraser, book, yes, a highlighter to highlight your answers, okay? So again, now back to classifying triangles. You've already learned one way to classify triangles this year, which was by their angle. So the first way that you see here on the board, by their angles, by the largest angle. And if you look on page 442, at the top, we have our three different triangles that we already learned this year. The first one is the wide obtuse triangle. That, of course, is a triangle that has at least one angle that is greater, wider than 90 degrees. So, for example, let me draw it up here for you. If we have one very long side and a smaller side, okay, then you can see that, well, you can kind of see that this is not a 90-degree angle. It cuts off to the left a little bit wider than a 90-degree angle. And so this is called an obtuse triangle. Obtuse triangle. Okay. Until now, we've mostly used the term obtuse angle. So this angle that is not very sharp, if it has one angle that is wider than a 90-degree angle, we can call that an obtuse triangle. Next, we have a right angle. That is a sharp 90-degree. It will have at least one sharp 90-degree angle, such as this one does. So we would call this one a right angle. Okay. And then there is the third type of triangle, which is what we call an acute angle. As in the class, we always joke and say it's a cute little angle. And this is where all the angles are less than 90 degrees. Okay. So they have the smallest angles. So the one that we show in our book kind of does something like this, where this almost looks like on the right here a 90-degree angle, but actually it is not. Instead of going straight up, it cuts off to the left. So every one of these angles is less than a sharp 90-degree angle. So we call these are acute angles, and in total it is an acute triangle. Okay, this part easy for us to understand. The rest is pretty easy too, don't worry. But then there is another way, instead of just looking at the largest angle to see which kind of triangle it is, we can also look at the lengths of the sides to see what they are. So if we have a triangle, and I really would need probably a ruler, but I'm going to do my best to make this perfectly the same. Okay, so we're going to at least pretend that all of these are exactly the same. And I know I did my best, but it's not perfect. And if every side is the same length, then this would be called not equal equal, but using the word, the beginning of the word equilateral triangle. And we learned earlier this year that this word lateral means side. So this means equal-sided triangle. Okay, this is where every angle is exactly the same size, equilateral triangle. Now there's another type of triangle called an isosceles triangle. And this is where two of the sides are exactly the same length and one is not. So in our book, we see something that looks like this, where this is a smaller angle and these two angles are a little bit wider, but these two sides, remember we're comparing them by the lengths of sides, so now two of these sides are exactly the same, and we call this ISOS, and then CELES, isosceles triangle. Okay, and then there is one more type of triangle and one more word that we have to learn today beyond that. So equilateral was all three sides. Isosceles, two sides are exactly the same. And so you might think, what would be the third type of triangle that when we compare triangles by the lengths of the sides? And maybe you would say, what I'm hoping you're thinking is that if no sides are the same, then we have what we would call a scalene triangle. So now this is not a 90-degree angle. It shoots off a little bit to the left. And then we have this very long bit here. And so you see this is just a little shorter, a little bit longer, or vice versa. I think I drew it exactly backward from your book. And then here we have this really long side, but none of these are exactly the same. So now we call this a scalene triangle. Okay, so take a look at what we have here. So we can classify triangles, name them by angles or by sides. Okay, and there is just one more term that you need to know today, which is equiangular. So if we have an equiangular triangle, what do you think that means? Right? Equal angles. Right? So let's see. Which of these triangles at the bottom have equal angles? Which one do you think? Is it the scalene? No. Is it the isosceles? Well, that one has two angles that are the same, since two of the sides are the same. Right, it's the equilateral triangle. If every angle, equilateral means equal-sided. So if every side is the exact same length, then this one is also an EQUI, angular triangle. Triangle. And I'm just going to put a triangle instead of the word. I'm running out of room. Okay, so now you have to think about one thing, which is that just because we can classify or name triangles these different ways, that doesn't mean that one particular triangle can't be called multiple things depending on what is happening with them. So in example 1 in your book, we are told to draw a triangle that is both a right triangle, so something like this, a right triangle, and an isosceles triangle. So in this case, it would be that two of the sides, well, we have to have one right angle, right? And then since an isosceles triangle has two sides that are equal length, we would be wise to begin by drawing a right angle with equal length sides. Okay, so I hope you see all of this clearly. There you go. And we are going to erase make a little bit of room up here for ourselves. Here. While I do this, continue to think about example number 1. Okay. My arms are getting a workout here, teaching from home. Okay, let's see. So it tells us in example number 1, remember we are on page 542. Example 1 says to draw a triangle that's both right and isosceles. We start with a right. We need a right angle. So here's our right angle. And an isosceles triangle means it has two equal sides. So those look just about perfect. And then we are going to connect it. So this is a right triangle. And it is isosceles. Okay, very good. It's not an acute triangle because all of the angles are not smaller than a right angle. So we can call that right and isosceles. Okay, so one is a right angle, the other two are cute little angles, acute angles. Okay, now in example 2, we have a triangle that is exactly the same, looks like same length, same sides, and we will take a look at that. Now we've moved on to page 543. And example 2. So we have something, this is going to be a little bit difficult to draw. Let's see, I think I'm going to go right about here. And then connect the sides, being very careful to make them just about as perfect as I can. The very best thing is to take out a ruler and draw each side exactly the same, starting with maybe the flat bottom. Okay. And then our book shows us, we can see, this is example 2, we can see that this triangle has all sides the same length. So it is, in fact, an equilateral triangle. So let's make note, equilateral, remember, equal-sided triangle, and I'm just going to put a triangle for the word triangle. We can look at the, so we've now looked at a word that we've known a long time, which was how comparing the sides. So it's an equilateral triangle, but what else is it? Okay, let's take a look at some of the angles and decide what kind of triangle it is based on the angle. Okay, the largest angle here. Well, it looks to me like this is an acute angle. This is less than 90 degrees, so it's an acute angle, and again, an acute angle. So since all of the since all of the angles are acute, we can call this an acute triangle as well. Okay, so that's two ways already that we can describe it. And then let's see, how about, could we use the word equa, but without the word lateral? Could we say equiangular? Okay, looks like if I drew all my sides perfectly the same length, like I was trying, and all of the sides are the same length, then it would appear that all of the angles are the same length. So we could also call this an whoops, made a little mistake there, equiangular triangle. Okay, so that's a third way already. And if you are looking in your book, you will see that this is also an isosceles triangle. So in looking at in figuring out the sides, trying to classify it by the sides, we not only can say that it's an equilateral, equal-sided triangle, but it's something else. So I'm going to group these two angle ones together. Acute, that where we looked at the angles, and now we're looking at the sides and seeing how many different ways can we classify this triangle based on the sides, right? And we see here that this is also, this can also be called an isosceles triangle because it has one particular thing that is very important to make it an isosceles triangle, which means that at least two, it could be more than two, it could be all three that are exactly the same, which would make it equilateral. But one step down from equilateral is isosceles. Isosceles, you might read isosceles triangle, because at least two, these two are the same, these two are the same, these two, no matter how you look at it, looking at the sides, it's an isosceles, but it's even more than that, it's an equilateral. Okay, looking at the angles, it's an acute triangle because all of them are, every angle is acute, and it's equiangular because they're all the same opening. All the angles are the same since all the side lengths are the same. All right, so that is your whole new concept part of our lesson. And now we're going to quickly do our lesson practice problems. So in letter A, it says, can a right triangle have two right angles? Why or why not? So on the back of your special paper that I sent home with the 6 boxes for 6 problems, I want you to continue on. You should have already done your mental math there, and now continue on with your lesson practice problems. Write small, because I want you to be able to, from now on, do your mental math nice and small there. Just take up a little section. Then I want you to be able to do, to follow along any notes on the, kind of in the middle of the page. And then I want you to be able to do your lesson practice problems at the bottom. So put a lot on that one paper, please. Okay, if you do need more paper than that, then label it well, title it well, and staple it to the back of that packet very neatly, okay? So lesson practice A, can a right triangle have 2 right angles? That is the question. Go ahead and do that problem and move on to B and C if you are really, really fast. Okay. Well, let's think about this. What if, let me make it a little straighter. What if I have a right angle like this? Can I have a second right angle? Could I do this and make it a triangle? I could not. I could not do that at all. If I did that, the sides would never meet, and so we do not have a triangle. It does not form a triangle. Okay, that's A. Let's look at question B. What is the name for a triangle that has at least two sides equal in length? And we already saw that that is, we just talked about that. So this question is just checking your understanding. So write isosceles triangle. Isosceles triangle. Okay. Letter C. Draw an acute scalene triangle. So in other words, draw a triangle that is acute and also scalene. Okay. Remember, acute means that all of the angles are acute. Doesn't mean that all the angle openings are exactly the same, but that they're all smaller than 90 degrees. The scalene part of it, if you look back on page 542, page before, you will see that scalene triangle. You'll be reminded that it has no sides that are the same length. Okay, so how could we draw an acute scalene triangle? Let's see, I think I'm going to start with the bottom straight. Okay, and I might be tempted to start with another line this way, but I can't. It has to be smaller than a 90-degree angle. So maybe I'll go this direction. Okay, and let's see. Now, how about we go this direction and see what happens? Okay. Well, that almost looks like a 90-degree angle. So maybe I need to come a little bit more pointy at the top. What if it's more like this? Kind of like that. Yeah. Doesn't form a 90-degree angle anywhere. We can see that this is a cute little angle, this is a cute little angle, and this is a cute little angle. And remember, a scalene triangle means that none of the sides are the exact same length. And you can see this one is shorter than that one, and this one looks kind of close though. Well, I might even, sometimes these take a little bit of work. I might even make this line a little bit longer to make sure that it looks longer than this one. So maybe I'll go even longer and then open it up this direction. Okay, how's that look? Again, kind of almost looks like a 90-degree angle. So this is a little tricky. Let me try again. Let's see. Got a long line here, shorter line here, and maybe an even longer line here. Something like that. So shorter, a little longer, and a little longer. Okay. You just want it to not look like a 90-degree. It's got to be a little shorter than a 90-degree. So maybe more like that. It's tricky. Okay, but it's acute. Let's see, maybe even cut it smaller, like that, maybe. Okay, so this looks smaller and smaller and smaller, none of them being exactly 90-degree. Well, all depends on how you draw it. You have to be careful. Okay, so let's move on to our star problems. Okay. All right. So our star problems begin on number 1. And you can see there on number 1 that there is no particular direction to write an equation, but it does say use the following information to answer parts A through C. So they are all related, A, B, C. So let's read it. Freeman rode his bike 2 miles from his house to Dee Dee's house. Together, they rode 4 miles to the lake. So let's think about that. Freeman rides his bike 2 miles and then gets to Dee Dee's house. Then they ride 4 miles to the lake. Dee Dee caught 8 fish. At 3:30 p.m., they rode back to Dee Dee's house. And then Freeman rode home. All together, how far did Freeman ride his bike? Okay, so this is one of those that it's best to draw a picture. Okay, so let's see if we can figure this one out together. So number 1, and keep in mind, we are on page 543. This is lesson 81, classifying triangles. Okay, so number 1, first star problem. So let's think about our friend Freeman. He starts somewhere and he rides his bike, let's say 2 miles. Okay, this is where a strategy comes in hand, and we know a bunch of different strategies that we have learned this year, and one of those is to draw a picture. So let's say he starts at his house and he goes 2 miles to his friend's house, let's say. All right, and then together they ride 4 miles to the lake. We don't know where the lake is, but let's just assume that they now go 4 miles, just double that, to the lake to catch some fish, right? Okay. Then they rode, oh, don't forget, Dee Dee caught 8 fish. Good for her. But do the fish have really anything to do with the question here? The first question will be, how far did Freeman ride his bike? So let's see. So Freeman went 2 miles. Then they both rode 4 miles to the lake. So let's write 4 miles. 2 miles plus 4 miles. Some fish were caught at 3:30. And then they rode back at 3:30, they rode back to Dee Dee's house. So let's see, this is Freeman's house. This is Dee Dee's house, right? So they're going to come back another what? 4 miles to Dee Dee's house, maybe have some fish, and then Freeman rides home. So now from here, he makes another trip this way, which we know is 2 more miles. So all together, how far did he ride? It was 2 plus 4 plus 4 back plus another 2 back. This is Freeman, who took every leg of this trip, every part of this trip. And then we can just start to add. Obviously 2 plus 4 is 6, plus 4 more is 10, plus 2 more is 12 miles. Well, they deserved the fish that they caught, didn't they? They did some exercising that day. Good for them. So 12 miles is our answer to part A. Okay. Now, I'm going to, well, you need to write that part down. Pause it if you needed to. And now let's move on to question B. Okay. Question B says, it took Freeman an hour and a half to get home from the lake. At what time did he get home? Well, think about that. What time did they leave the lake to go back to Dee Dee's house? Well, they were at the lake, and our story told us that at 3:30 he left Dee Dee's house. I'm sorry. At 3:30 they left the lake to go back to Dee Dee's house. Okay, and then it said it took Freeman an hour and a half to get home from the lake. At what time did he get home? So from the time he was at the lake, it was another hour and a half. So let's add 1 hour. That would be 4:30. And another half an hour. That would be 5. Is it early in the morning, do you think? No. Most parents would not let their kids go fishing at the lake by themselves with a friend at 3:30 in the morning to 5 in the morning. So it makes the most sense that it would have been in the afternoon anyway, but we were told at the very beginning that it was 3:30 p.m. So look for clues like that as you do your problems. All right, so that brings us to number 2. The next star problem is number 2, which says, describe the number of degrees and the direction of a turn that would move this letter B to an upright position. Okay, well, let's draw the letter B as it sits right now. Go ahead and draw that in box number 2. Okay, and let's think about that. It says, let me read it again. Describe the number of degrees and the direction of a turn that would move this letter B to an upright position. Okay, so we talk about directions around a circle or an object. We talk about it as clockwise, which if you think about a clock, like 12 o'clock, 3, 6, 9, the clock hands move this way. We call that clockwise. So we can attempt to turn this B clockwise, like it's facing this way right now. Look at the top of the B, and we can turn it to face this way with just 1/4 turn, right? And 1/4 turn, it's sort of like this clock here. If it's pointing this way, and now it's going to move up straight. So just look at the top of the letter, and we can see that clockwise, so in the direction of the clock going this way, we did 1/4 turn, and 1/4 turn is the same as 90 degrees. So we can go clockwise 90 degrees to lift this B and make it, put it vertical. But what if we were going to go the other way, counterclockwise? Counterclockwise. Okay, and take a look at this. Clockwise is one word. Counterclockwise, it has 3 base words, basically, and yet it's just written as one word, counterclockwise, no hyphens or anything. So let's take a look. Let's go back to our B. Let's now draw it again without all of this. Okay, now we are not going in this direction anymore. We are going to go counterclockwise. Counter means against, so against the normal path of a clock. And so if we were to turn this B, right now it's turning this way. If I wanted it to turn where this is the bottom, then I would need to make 1 turn down. So now the B would look like this, and this would be the top of it, right? So I'm turning it to the left, and now I would turn, so first there was this 90 degrees. Now that the B would be facing down, now I would turn it where the head of it is this direction, which would be another 90 degrees. And that would look like this, right? And then I'm still trying to stand it up. So now I have 90 degrees, 90 degrees, and the B, the top of the B is facing that way. So I'm going to turn it another quarter turn, or another 90 degrees, to now force this B to face upward. And that's 90 plus 90 plus 90, which is the same as like 9 times 3, add a 0. And that is 270 degrees if you were turning it counterclockwise. Okay, so clockwise was 90, counterclockwise was 270 degrees. Okay, and there you are. Feel free to pause it if you need to see it for longer to write it down. Hopefully you are working quick, and you are keeping up with me the best you can. All right. Number 5. Find the length of this segment to the nearest quarter inch, the question asks. Find the length of this segment to the nearest quarter inch. Okay, so take a look at that inch scale. Okay. Can you see that the segment, that little line, goes past the 3 but not to the 4? So it's somewhere after 3. Number 5, it's 3 and something, and we're looking for those quarter inches. So is it 3 1/4, 3 1/2, 3 3/4? So 1/4, by the way, this is the same as 2/4, right? 3 1/2 is the same as 3 2/4. So is it closer to 3? We can back up a little bit even. Is it closer to 3, 3 1/4, 3 2/4, which is the halfway mark, or 3 3/4? So let me take a good look at this. It says to the nearest quarter of an inch. It looks to me like it is closest to this, to 3 1/2 inches. So let's write 3 1/2 inches. I wrote that a little close. 3 1/2 inches. Okay, or you could have said 3 2/4 inches. Either one is right. All right, and it is also right if you just simply said IN, lowercase IN, with the decimal point, which is the shorthand way to write inches. All right, let's see what's next. Jonathan, what's next? I wish you were here. I wish you were all here. Or that we were in class together. That'd be great. But number 8, write an equation to show how to convert any number of ounces to pounds. Use 0 for ounces and P for pounds. I'm glad I could help you with this. We already learned, let's see. Let's see, here's what we would say. We could have a certain number of ounces and then we can say equals, the ounces equals 16 pounds, 16p. That would be one of the equations. Or you could say 16 P equals 0. Okay. All right. So write that down. And number 9 says, what fraction of the set of triangles is shaded. Okay, so here we see that there are 5 equal parts, 5 identical triangles, and we see that 2 of them are shaded. So 2/5 is our answer for that one. Okay, let's go on to number 11. I have some room, so I'll just do it here. Number 11, which is a multiplication problem. It says 31 times 20. Now, we could write 31 times 20 just like this, and then do 2 lines of answers that we then add together. But we're still in 4th grade, so we're going to take a shortcut. And instead of writing it this way, we're going to write it as 31 times a multiple of 2, 31 times 20. And we will do the more simple multiplication and then add that 0 at the end. So 2 times 1 is 2, 2 times 3 is 6, and just simply bring down the 0, and your answer is 620 for number 11. Let's do number 13 together. Number 13, another similar problem. Always look for those multiples of 10, such as the 50 in this problem. We have 25 times 50. I'm going to leave that 0 off to the side to make it easy for me. 5 times 5 then is 25. 5 times 2 is 10 plus 2 is 12. And just drop that 0 that's hanging off to the side. And we have 1,250 as our next problem. Let's see. Okay, number 20. Let's move on to number 20. Do not forget, you can always pause if you feel like I'm going a little too fast. Number 20, which of the following is equivalent to 1/2? So in this problem, we have a rectangle that is shaded on one side, and we want to know which is an equivalent number to 1/2. Well, is 1/3 equivalent? No. Is 2 out of 6 equivalent? No, that's the same as a third. And then we have 1/4. No, that would only be like part of this. So that doesn't work. So our answer is 2/4 is equivalent. Remember to put a box around your answers and to highlight your answer, which would be the 2/4, in yellow or pink or some other light, bright color that I can see through easily. Okay, moving on, we have number 22 as our next problem. Number 22, which says if y, let's write this down for ourselves, if y, write it in your box, equals 2x plus 3, then what is y? The question is, this is a question, what is y? Okay, but I'm going to move back up here. What is y when x is 1 or 2 or 3? 1, 2, and 3. So if you remember this, this formula, this equation, this is a graphing equation. So we could even put a table off to the side. We learned how to do this, x and y, and we could figure this out. So when x is 1, 2, or 3, the question is, what is y? So you see, we're going to have quite a bit of work to do here to figure this out, but it's pretty easy. So now we're going to replace this x with this 1. So we're going to say y equals 2 times 1. Notice I put that into parentheses. 2 times 1 plus 3. I could have just said 2 times x plus 3, but to me this is really nice and clear. And then we continue on using, of course, our order of operations, which we went over 2 lessons ago last week, which said parentheses, I get to go first, right? Always check for parentheses. Here we had one, so the very first thing we're going to do is take whatever that is and multiply it. 2 times 1 is 2, and bring down the rest. And y then is 5. 2 plus 3 is 5. So we've just figured out that when x became 1, we replaced the x with 1. We substituted this. Then y at the end is 5. And we'll see a pattern form in just a moment. Okay? So you need to have all of this written down just like your teacher does now, okay? Now I'm going to erase everything plus that 1, except you're not erasing, you're just going to redo it. Actually, I'll erase it all so you can follow along with me. So now you're writing this again. Okay, I don't have the room to write it 3 times like we need to do 3 different simplifications. So let's get going, and we're going to substitute a 2 in place of that x. So 2 times the 2 now plus 3. Parentheses goes first. 2 times 2 is 4. Bring down the rest, which is the plus 3. And we see that when x was 2, y became 7. Okay, I think we can see a pattern forming. And our next number, let's see, 5 plus 2 was 7. My guess is that the next number is going to be 9. How about you? Let's see. Okay, so now rewrite this problem again for the 3rd time. If y equals 2x plus 3, but this time we are replacing that mystery letter x with a 3, then we have 2 times 3 plus 3. Parentheses first, we have 2 times 3, not 2 plus 3. 2 times 3 is 6 plus 3, and check it out. The pattern is continued, and we have 5, 7, and 9. Now, this particular problem did not ask us to graph it, but guess what? Letter B does. It says use lesson activity 8 and graph y equals 2x plus 3 on a coordinate graph. So what that means is that you could have basically to use graph paper. Well, you or I don't have graph paper right now, and we don't need it really. We can remove all of our work to find out what y was right here, and we'll leave our table here that told us what x and y was, and we will remember that when we graph, we can have a coordinate pair like this inside of parentheses x and y. So in the first coordinate pair, we would have 1, 5, then 2, 7, and 3, 9. So let's just draw our own graph here, a coordinate plane. This area is our coordinate plane. We will have our arrows to indicate that these lines go on forever. This pattern would continue. If we continued the pattern of 5, we'd have 11, and so on. And let's draw it. We know that the origin, this point right here, is where we start with 0. This would be the coordinate point 0, 0. We remember that we had learned that this line is the x line, and this is the y line up here, x and y. And so let's see, we have to look at what numbers we have. We have numbers 1 through 9 that we have to graph. So we can count by twos like we did in a lesson 2 lessons ago, lesson 80, or we could just go by 1, 2, 3, 4, 5, 6, 7, 8, and 9. So that brings me to 9, 1 to 9. And we will go ahead and number it. Okay, and remember, each of these have to be equal parts. I know mine isn't perfect, right? And then, so I'm going to draw 1, 2, 3, 4, 5, 6, 7, 8, 9 on the y-axis. We call it the x-axis and the y-axis. Okay. And we are going to graph our first point. Our first ordered pair or coordinate pair, first ordered pair is 1, 5. Oh, I almost forgot to number these, sorry. Okay, you can see that all the numbers that we are graphing to are there, so that should be perfect. So let's go 1 to the right. The x tells us to go 1 to the right, and then on the y side we are to go up to 5. So if you could be really careful, go to the right 1 and up 5. And this is the point 1, 5. Can you see that okay? I hope you can. 1, 5. There's the point 1, 5. Now let's do 2, 7. X is 2, so we go 2 to the right, and we go up to 7. And right here, we're going to label it. This is coordinate point 2, 7. Okay, now we go to our third ordered pair, which is 3, 9. So right 3, up 9, right here. There is 3, 9. And we have now graphed all of these. But I want to take it just one step further, just for fun, which is to go ahead and connect them. So let's start with 1, 5. Go to 2, 7, and go to 3, 9. And you can see that that original formula that we had, y equals 2x plus 3. When we know the x's, we can figure out the y's and so on. And then this will always become a line. Okay, how fun. All right, so take a good look at that. Make sure you have this down in your box for number 22. And I'm going to erase it now. Okay, so that was number 22. Let's see which is the next star problem. Number 24. Says find the perimeter and the area of this rectangle. Okay, so we have, first of all, a rectangle that this isn't perfect, but something like this. This should have actually been half the length here. I made it a little bit too long. Okay, so about like that. 20 inches by 10 inches is our rectangle. The perimeter, so we have two things to figure out, the perimeter and the area. Perimeter, of course, is when you add up all the distances, all the lengths, I could say, of every side, right? So we can say that's 20 plus 20, these two sides, inches plus 10 inches, right? Don't forget that we'll have inches at the end. So 20 plus 20, 40, plus basically 20 more. The perimeter is 60 inches on this problem, okay? So now that brings us to our area, right? So the second half of this problem is our area. Our area, we know area is the length times the width. So we are going to multiply 20 times 10. The length is the longer side, of course, 20 inches by 10 inches. And here you can see that it is important to keep the inches in there because we're going to have basically a separation of 20 boxes one direction and 10 the other direction. I'm not drawing it perfectly. So what we're trying to figure out with area is the measurement of how many squares are inside of our rectangle. So we could, of course, just say 2 times 1 is 2. Add the number of zeros that we have in this problem, which is 2 zeros. And we have 200. Now the inches really matter on an area problem. We have to, because it is how many square inches we have. So we can say 200 inches squared, or we could say 200 square inches. There's a second way to write it. So there's several ways. There's like at least 3 ways to write that. So could you please have at least one of those and this? So the perimeter is 60 inches. The area is 200 inches squared, or 200 square inches. Okay, let's see, what other problems do we have? We have number 27 as our last star problem for today. So let me do that problem for you, and then the rest you can jump on to doing for homework, the star problems. So number 27 says, in this polygon, remember that means multiple-sided, enclosed, a closed figure that is a flat figure. It's not a three-dimensional object like a cube. So in this polygon, which side appears to be parallel to side AB? So we have something that looks like this. Here's angle A, angle B. Okay, angle AB, C, and D. And we want to look at which side is parallel to side AB. So here is side AB, and the only one that runs the exact same direction and will never cross it. This line crosses it. This segment is going to cross it this way. These are segments, not lines, because they don't go on forever. Excuse me. So the only one that is parallel to this one is, of course, this one here that I'm now turning into red. And so what our answer to this problem is side CD, or you could call it side DC. It doesn't matter whether you go left to right or right to left. If it's the same segment, that is the exact same name, just switch the letters. All right, well, that gets us through all of our star problems, all of our lesson 81. I hope you enjoyed it. I think there is much to learn and much to remember. And the next thing you will do is probably Friday, so tomorrow, after you do all of your non-star problems with help from a parent, and again, reach out to me if you have specific questions that you can't get answered, because all of your homework will be graded from now on for accuracy, for getting them right. So if you want to get a really good grade, make sure you get that help. You really do need it, especially after it's been a few weeks of not working together. Okay, what else did I want to say? Oh, very important, which if you do see this video early in the day, I'm not sure when you're going to watch it, but I have placed bandanas. Here's mine. There's many different kinds, and I would like you to wear it to the Zoom meeting that we have on Friday at 11 o'clock. And you can wear this any way you want. You can make it a mask like a lot of people are wearing because of the coronavirus pandemic, or you could wear it like a bandit or whatever. But we will see you guys on Friday at 11 a.m. again this week for our Zoom meeting, where we will briefly talk about how you're enjoying By the Great Horn Spoon and get to see each other just for fun. If you can't do it, it's not the end of the world. We will miss you, but hopefully all 17 of you and I and Mrs. Conklin will be there with our By the Great Horn Spoon bandanas on. So enjoy your day. Love you guys. Bye.